we're going to gently unfold a question that sounds almost childlike in its simplicity. How big is the solar system, really? It's a question that seems like it should have a neat answer, perhaps a number you could write down, something tidy and satisfying. But as we move through it together, you may begin to notice that the idea of size in space is not quite as straightforward as measuring a room or even a country. Distance stretches in unfamiliar ways out there. Familiar reference points fade. The mind tries to hold on to scale, and then, very gradually, lets go. Before we begin, I'd like to ask you something simple. Where are you listening from tonight? And what time is it in your part of the world right now? Maybe it's late evening and the day is winding down. Maybe it's very late, and the quiet has already settled in around you. Wherever you are, I'm glad you're here for this gentle journey outward. If you find this kind of slow, curious exploration soothing, or simply a pleasant way to unwind, you might consider liking the video or subscribing. It helps this calm little corner of science reach others who are also looking for something thoughtful and relaxing at the end of the day. Now let's begin by imagining something familiar. Picture yourself standing outside on a clear night. The air is still. Above you, the sky's scattered with stars, some faint, some bright enough to catch your attention immediately. Somewhere up there, invisible to your eyes, are the planets of our solar system, each following its quiet path around the sun, each separated from the others by distances so large that they almost resist imagination. We often talk about the solar system as if it were a kind of collection, a group of objects gathered together in space, like fruit in a bowl or houses along a street. There's the sun in the middle, then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and beyond them smaller worlds, icy fragments, distant clouds of debris. It sounds organised, almost compact, as though everything is neatly arranged. But the truth is very different. The solar system is not crowded. It is not tightly packed. In fact, it is overwhelmingly empty. That emptiness is the first clue to understanding its true size. You see, when we look at diagrams in books or animations online, the planets are often shown fairly close together. This isn't because they really are close together, but because if the distances were drawn accurately, the planets would be so far apart that the diagram would need to be impossibly large. You might see Earth drawn a few centimetres from the Sun on a page, and Jupiter perhaps a short distance farther out. But in reality, if the Sun were the size of a large exercise ball, Earth would be a small bead many metres away, and Neptune would be so far off that you might lose sight of it entirely. Our minds are not used to scales like this. We live in a world where walking a few kilometres feels like a journey, where driving across a country can take hours, where crossing an ocean takes a day in an airplane. These distances feel large to us because they are large on a human scale. But in the solar system, even the vast distances between continents would shrink into insignificance, smaller than the thickness of a line on a map. And yet, despite how enormous the solar system truly is, we live right in the middle of it, moving through it constantly, carried along by Earth's orbit without ever feeling the motion. Right now, as you listen, the planet beneath you is travelling around the Sun at about 30 kilometres per second. That's over 100,000 kilometres per hour, fast enough to circle Earth more than twice in a single hour, and yet completely imperceptible. The ground feels steady. The air feels calm. Time moves at its usual pace. It's one of those quiet reminders that motion, like size, often depends on perspective. Thinking about scale in space requires a small adjustment in how we imagine distance. Instead of meters or kilometers, astronomers often use something called an astronomical unit. One astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. That may sound like a large number, and it is, but it's also a useful stepping stone, a way to make the vastness of the solar system slightly easier to describe. Mercury orbits at about 0.4 astronomical units from the Sun, Venus at about 0.7 astronomical units. Earth, of course, sits at 1 astronomical unit. Mars is around 1.5 astronomical units away. At first, those numbers seem manageable, almost close together, like neighbouring towns along a highway. But then we continue outward. Jupiter orbits at about 5 astronomical units. Saturn at about 9.5 astronomical units. Uranus at roughly 19 astronomical units. Neptune at about 30 astronomical units. Each step outward multiplies the distance, stretching the scale farther and farther until the inner planets feel clustered together near the Sun like grains of sand near the centre of a vast empty field. What's interesting is that even these numbers don't fully capture the feeling of distance. Numbers can be precise, but they don't always feel real. To really sense the scale, it helps to think in terms of travel time. Light, the fastest thing in the universe, takes just over 8 minutes to travel from the Sun to Earth. That means the sunlight you see right now actually left the Sun 8 minutes ago. If the Sun were to suddenly disappear, which fortunately it won't, we wouldn't know for 8 minutes. To reach Jupiter, sunlight takes about 43 minutes. To reach Neptune, it takes more than 4 hours. Imagine that for a moment. A beam of light, moving at nearly 300,000 kilometers per second, still needs hours to cross the solar system to its outermost major planet. That begins to give a sense of the scale we're dealing with. Another way to think about it is to imagine shrinking the solar system down to a more familiar size. Suppose the Sun were the size of a coin placed on a large field. Earth would be a tiny speck several meters away. Neptune would be hundreds of meters distant, and between them, almost nothing. Just space, silent and empty. That emptiness is one of the defining features of our cosmic neighbourhood. Space is not filled with swirling clouds or glowing light most of the time. It is mostly vacuum, with only occasional particles drifting through. The planets are islands in a vast, dark ocean. And yet, even calling them islands might be misleading, because islands suggest proximity, the possibility of seeing one from another on a clear day. In the solar system, the distances are so great that if you stood on one planet, the others would usually appear as little more than bright points of light, indistinguishable from stars to the naked eye. It's a quiet kind of vastness, not dramatic or overwhelming in the way mountains or storms can be, but subtle, patient, stretching outward in every direction. Sometimes, it helps to pause and reflect on how recently humanity has begun to grasp this scale. For most of history, people believed the planets were small lights, embedded in a crystal sphere surrounding Earth. The sky felt close, intimate, almost within reach. It wasn't until the last few centuries that we began to understand just how far away those lights truly were. Even now, our intuition struggles to keep up. Think about the moon for a moment. It feels close, familiar, part of our everyday experience. And in cosmic terms, it is close. The moon is about 384,000 kilometers away. Light takes just over 1 second to travel that distance. Astronauts reached it in a few days, but compared to the rest of the solar system, the moon is practically in our backyard. It's the first small step outward, the nearest marker on a journey that quickly becomes far more expansive. As we move farther from Earth, distances begin to grow not just large, but immense. The gaps between worlds widen. Travel times stretch from days to months, then to years. Signals sent from spacecraft take longer and longer to reach us, until conversations with distant probes unfold with minutes or even hours between each reply. There's something quietly humbling about that. It reminds us that the solar system is not a compact arrangement of worlds, but a sprawling, sparsely populated region of space, bound together by gravity yet separated by enormous distances. And yet, despite that vastness, everything within it is connected. Every planet, every asteroid, every comet is held in orbit by the Sun's gravity, all of them moving together through the galaxy like a slow, silent caravan. If you imagine the solar system not as a cluster, but as a wide, gently rotating disk, with the Sun at its centre and the planets tracing enormous circular paths, the scale begins to feel more natural. Not small, not crowded, but expansive and calm. Right now, Earth is on one of those paths, carrying oceans, continents, cities, forests, and all of us along with it. We rarely think about it, but we are travellers in space, moving through a vast system whose true size is far greater than it first appears. And that realization opens the door to a deeper question. When we ask how big the solar system really is, what exactly are we measuring? Are we talking about the distance to the farthest planet, the edge of the Sun's gravitational influence, the boundary where the solar wind fades into interstellar space? When people hear the words the solar system, most of us picture something fairly simple. There's the sun in the middle, the planets arranged in order, maybe a few rings and moons, and beyond that, well, a vague sense of space fading into darkness. It feels like a neat, defined place, almost like a map with a clear border drawn around it. But if you pause for a moment and think about it, that idea of a border becomes a little uncertain. Where exactly would you draw the line? At the orbit of Neptune? At the farthest known dwarf planet? At the point where the sun's gravity finally loses its influence? Or somewhere even farther out, in regions we've never directly seen? It turns out that the solar system doesn't have a single, tidy edge. Instead, it fades outward gradually, like the glow of a campfire dimming into the night. To understand what we mean by the solar system, it helps to start with the most obvious part: the sun itself. The sun contains more than 99.8% of all the mass in the solar system. Everything else, every planet, moon, asteroid and comet combined, makes up only a tiny fraction of what's here. In a sense, this solar system is really the sun's domain, the region of space where its gravity shapes the motion of objects around it. Gravity is the key idea here. The solar system is not defined by visible boundaries, but by influence. Anything that orbits the sun or is strongly controlled by the sun's gravity is part of the solar system. That sounds straightforward at first. The planets clearly orbit the sun, so they're included. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each follows its own path, taking months or years to complete a single circuit. But already, even at this level, things begin to feel more complex than the simple textbook picture. The planets are only the most visible members of a much larger family. Each planet is surrounded by moons, sometimes dozens of them. Jupiter alone has more than 90 known moons, some large enough to be planets in their own right if they orbited the sun directly. Saturn's rings, which look so smooth and elegant from a distance, are actually made of countless individual pieces of ice and rock, each one orbiting Saturn like a tiny world. And then there are the asteroids, thousands upon thousands of rocky fragments, most of them orbiting between Mars and Jupiter in a region known as the asteroid belt. Some are small as pebbles, others, like Ceres, are hundreds of kilometers across and nearly spherical. Beyond that lie comets, icy travellers that spend most of their time far from the sun, only occasionally sweeping inward, growing bright tails as sunlight warms their surfaces. All of these objects are part of the solar system, even though many of them are rarely mentioned in simple diagrams. The solar system is not just planets. It is a vast population of bodies of many sizes, most of them small, most of them invisible to the naked eye. And still, that's only the beginning. Because the solar system also includes things you cannot see at all. This solar wind, for example, is a continuous stream of charged particles flowing outward from the sun in all directions. It moves through space, filling the region around the sun with a thin, invisible plasma. That flow extends far beyond the orbits of the planets, forming a kind of enormous bubble around our star. This bubble, called the heliosphere, stretches far into space, much farther than Neptune, much farther than Pluto, reaching distances so large that sunlight itself takes many hours to travel across it. Inside that bubble, the sun's influence dominates. Outside it, the space between the stars begins. So one way to define the solar system is to say that it extends as far as the heliosphere, as far as the solar wind can reach before it is slowed and pushed back by the thin gas of interstellar space. But even that may not be the final edge. Far beyond the planets, beyond the region where most comets originate, astronomers believe there may be a vast spherical cloud of icy objects surrounding the sun, at distances tens of thousands of times farther than Earth is from the sun. This region is called the Oort cloud, and although we cannot see it directly, there is strong evidence that it exists. If the Oort cloud is real, then the solar system extends astonishingly far, perhaps halfway to the nearest stars. In that sense, the solar system is not a small neighbourhood at all, but a huge diffuse region stretching across distances so large that the inner planets would seem like a tiny speck near the centre. This brings us to an interesting point. The solar system is not a solid thing. It is not a sphere or a disk with clear edges. It is more like a gradient, a gradual thinning of object and influence as you move farther outward. Closer to the sun, matter, is more concentrated. Planets, moons, asteroids, dust and gas are relatively common, at least by cosmic standards. Farther out, objects become fewer and farther between. Eventually, the sun's gravity becomes so weak that passing stars and the tides of the galaxy begin to compete with it. At that distance, it becomes difficult to say exactly where the solar system ends and interstellar space begins. There is no sharp boundary, no signpost announcing that you've crossed from one region to the other. There is only a gradual transition, a fading of one environment into another. Another way to think about it is to imagine standing at the edge of a forest at night. The trees grow thinner and thinner, until eventually there are only a few scattered trunks, then none at all. Where did the forest end? At the last tree? Or at the point where trees became rare? The answer depends on how you choose to define it. The solar system is like that forest, and definitions matter, because depending on which one you use, the size of the solar system changes dramatically. If you define it as the region containing the planets, it extends to about 30 astronomical units, the distance of Neptune. If you include the Kuiper belt, where Pluto and many icy bodies reside, it stretches to perhaps 50 astronomical units or more. If you include the heliosphere, the solar wind bubble, it reaches more than 100 astronomical units in some directions. And if you include the Oort cloud, the solar system may extend tens of thousands of astronomical units, a distance so vast that it becomes difficult to comprehend. At that scale, the solar system is no longer something you could easily draw on a page or even model on a football field. It becomes something more like a region of space, diffuse and expansive, defined more by influence than by structure. There's also another subtle point worth considering. The solar system is not stationary, it is moving. Our sun orbits the centre of the Milky Way galaxy at a speed of about 220 kilometers per second. As it travels, it carries the entire solar system with it. Planets, comets, dust, and all. So the solar system is not just a set of orbits around the sun, it is also a moving bubble, drifting through the galaxy, passing through regions of varying density and radiation. That motion adds another layer to the idea of what the solar system is. It is not just a place. It is a travelling system, a moving environment shaped by both the sun and the wider galaxy around it. Sometimes it helps to step back and appreciate how extraordinary it is that we can even ask these questions. Just a few centuries ago, people did not know the true distances to the planets, or even that other stars were suns like our own. The idea of the solar system as a vast, structured region of space is a relatively recent discovery, and even now, our understanding continues to evolve. New dwarf planets are discovered, new comets are tracked. Spacecraft venture farther than any human-made object has gone before, sending back data from regions once thought unreachable. Each new piece of information helps refine our picture of the solar system, making it clearer, but also revealing how much more there is to learn. So when we ask how big the solar system really is, we're also asking what we mean by it. Are we measuring the region of planets, the reach of the solar wind, the outermost icy bodies held loosely by the sun's gravity? So let's begin close to home, with something solid and familiar, something we can actually picture without straining the imagination too much. Before we try to grasp the size of the solar system, it helps to anchor ourselves to a scale we understand. And there is no better starting point than the planet you're sitting on right now. Earth feels large to us. Oceans stretch beyond the horizon. Flights between continents take many hours. Crossing an entire country can take days by car. For most of human history, the world felt almost immeasurably vast, a place so big that exploring it took lifetimes. And yet, from a cosmic perspective, Earth is small. Not just small in a poetic sense, but physically small, a sphere about 12,742 kilometers in diameter. If you could drive straight through the planet from one side to the other, ignoring the rather impractical detail of molten rock in the way, you would travel a distance roughly equal to the width of the continental United States. That's large on a human scale, certainly, but compared to the distances between worlds, it's only the first tiny step. One useful way to understand Earth's size is to compare it with something we can experience more directly. Travel time. A commercial airplane moves at around 900 kilometers per hour. At that speed, flying halfway around the world takes roughly 10 hours. To circle the entire planet would take about twice that, not counting layovers, delays, or the small but inevitable wait at baggage claim. Now imagine shrinking Earth down to the size of a marble. Not a very tiny marble, perhaps one about 2 centimetres across. At that scale, a passenger jet would be far too small to see, and the tallest mountains would be little more than fine texture on the surface. Holding that marble in your hand, it would be easy to forget that it represents everything familiar, every city, every forest, every ocean, every person who has ever lived. The entire human story compressed into something that could roll under a sofa and disappear. Thinking this way helps reset our sense of scale. It reminds us that even the largest things in our everyday experience are small compared to planetary and cosmic distances. Another way to appreciate Earth as a reference point is to think about gravity. Earth's gravity feels strong to us because we live within it constantly. It holds the atmosphere in place, keeps oceans from drifting into space, and gives weight to everything we touch. But Earth's gravitational influence extends far beyond the surface. In fact, it stretches tens of thousands of kilometres into space, gradually weakening with distance. Satellites orbit within this region, some only a few hundred kilometres above the ground, others much farther away. The International Space Station, for example, orbits at about 400 kilometres above Earth's surface. That sounds high, and it certainly is by aviation standards, but on a planetary scale it's barely above the surface at all. If Earth were the size of a basketball, the space station would orbit less than a centimetre above it. That comparison often surprises people. Space, at least the region where most spacecraft operate, is much closer than it feels. Even the boundary where Earth's atmosphere fades into space, sometimes called the Kármán line, is only about 100 kilometres above sea level, a distance that, if you could drive straight upward, you might cover in little more than an hour. So in a sense, space begins not far above us. The vastness we're trying to understand starts surprisingly close to home, and yet despite that proximity, the moment you leave Earth behind, distances begin to grow very quickly. It's interesting to consider how humans first measured the size of Earth itself. Long before satellites or GPS, ancient astronomers used careful observation and simple geometry. One of the most famous examples comes from Eratosthenes, a Greek scholar who lived more than 2,000 years ago. He noticed that at noon on the summer solstice, the sun shone directly down a well in the city of Syene, casting no shadow. But at the same time in Alexandria, a vertical stick did cast a shadow. By measuring the angle of that shadow and knowing the distance between the two cities, he calculated the circumference of Earth with remarkable accuracy. It's a quiet reminder that understanding scale doesn't always require advanced technology. Sometimes it begins with curiosity, patience, and careful thought. From Earth's size, we can begin to build outward, using our planet as a measuring stick. Astronomers often use Earth's diameter, or the distance from Earth to the Sun, as reference points, stepping stones that help bridge the enormous gaps between objects in space. And those gaps grow faster than most people expect. For example, if Earth were shrunk to the size of a marble, the Sun would not be nearby at all. It would be a sphere about 2 meters wide, placed roughly 200 meters away. That's about the length of 2 football fields. Between the marble and the large sphere, there would be almost nothing, just empty space. That emptiness is one of the defining characteristics of the solar system. It is not a crowded place. It is mostly space, with small islands of matter scattered here and there. Another way to approach this idea is to think about light again, because light gives us a kind of universal ruler. Light travels incredibly fast, about 300,000 kilometers per second. It can circle Earth more than 7 times in a single second. And yet, even at that speed, it takes time to cross the distances we're talking about. Light takes about 1/10 of a second to circle Earth once. That's quick enough to feel instantaneous, but already that tiny fraction of time hints at how large the planet really is. Signals sent to satellites in high orbit take noticeable fractions of a second to return. Engineers must account for these delays when controlling spacecraft. Even communication across Earth's surface, through fibre optic cables and radio signals, is not truly instantaneous. It feels that way, but physics quietly reminds us that nothing moves infinitely fast. Using Earth as a reference point also helps us understand something else: how thin our environment really is. The atmosphere, which feels vast when you look up at the sky, is actually very shallow compared to the size of the planet. Most of the air we breathe is contained within the first 10 or 15 kilometres above the surface. Beyond that, the air becomes thinner and thinner until it fades into near vacuum. If Earth were the size of a globe in a classroom, the breathable atmosphere would be thinner than a layer of varnish on its surface. That fragile thinness adds another layer of perspective. Everything we depend on exists in a narrow shell surrounding a small planet, orbiting an ordinary star in a system that extends far beyond our everyday awareness. And yet, despite how small Earth is in cosmic terms, it is still large enough to feel enormous to us. That contrast is part of what makes understanding the solar system challenging. We must hold two ideas at once, that Earth is vast on a human scale and tiny on an astronomical one. Sometimes it helps to imagine shrinking yourself rather than shrinking the planet. Imagine you're standing on a plane and the Earth beneath you expands until its curvature becomes obvious, until continents and oceans spread out like patterns on a giant sphere. Now imagine rising upward, higher and higher, watching the planet shrink below you. At first, cities fade, then coastlines blur. Eventually Earth becomes a blue and white marble suspended in darkness, small enough to hide behind your thumb. Astronauts have described this experience as both awe-inspiring and strangely calming. From that distance, the borders and divisions that seem so significant on the ground vanish completely. There is only one world, one atmosphere, one fragile sphere of life. That image, sometimes called the overview effect, changes how people think about Earth's place in the universe. It transforms the planet from something vast into something delicate, almost intimate. Because as soon as you leave Earth behind, even the nearest distances begin to stretch beyond what feels comfortable to imagine. Using Earth as our reference point helps us build intuition gradually, one layer at a time. We begin with something we know, something we can picture, and then extend our understanding outward in stages, like stepping stones across a wide river. It's a patient process, and it rewards patience. The more slowly we approach these distances, the more clearly they begin to make sense. Let's move outward now, but only a little, because the first step away from Earth is both modest and astonishing at the same time. Our nearest neighbour in space, the Moon, has been part of human life for as long as people have looked up at the sky. It feels familiar, predictable, almost companionable, rising and setting in its steady rhythm, changing shape night after night in a cycle that guided calendars, harvests and stories for thousands of years. And yet, despite that familiarity, the Moon is far away, much farther than most people instinctively imagine. If you were to get into a car and drive toward the Moon at highway speed, say around 100 kilometers per hour, without stopping to refuel, rest or sleep, it would take you more than 5 months to arrive. Even a jet aircraft flying far faster than any car would need several weeks to make the journey. Light, travelling at the fastest speed possible in the universe, takes just over 1 second to cross the distance between Earth and the Moon. That may not sound like much, but it's long enough that astronauts on the lunar surface experienced a slight delay in radio conversations. When someone on Earth asked a question, there was always a small pause before the reply came back, a reminder that even at the speed of light, space is not truly small. The average distance to the Moon is about 384,000 kilometres. Numbers that large can feel abstract, so it helps to translate them into something more tangible. Imagine Earth as a globe about 1 metre in diameter, roughly the size of a large exercise ball. At that scale, the Moon would be about the size of a tennis ball placed nearly 30 metres away. That's about the length of a swimming pool, or the distance across a wide city street. Between the globe and the tennis ball there would be nothing. No dust, no rocks, no air, no faint glow, just empty space. That emptiness is the first thing people notice when they begin to grasp the distance to the Moon. The Earth and Moon are often shown close together in illustrations, sometimes with only a small gap between them, but in reality they are separated by a vast stretch of vacuum. There's a fascinating fact that helps make this clearer. All of the planets in the solar system could fit in the space between Earth and the Moon, lined up side by side, and there would still be room left over. Jupiter alone would take up a large portion of that space, but the remaining planets together would still fit comfortably within the gap. It's one of those comparisons that quietly reshapes your sense of scale. The distance to the Moon, which feels modest on an astronomical scale, is already enormous compared to the sizes of the worlds themselves. The moon's orbit is not perfectly circular, so its distance from Earth changes slightly over time. At its closest, called perigee, it comes within about 363,000 kilometres. At its farthest, called apogee, it can be more than 405,000 kilometres away. That variation is large enough to affect how big the moon appears in the sky, giving us what people sometimes call a supermoon, when it's slightly closer and brighter than usual. Even so, these changes are small compared to the overall distance. Whether near or far, the moon remains a remote world, separated from us by a gulf that only a handful of humans have ever crossed. When the Apollo missions travelled to the moon in the late 1960s and early 1970s, the journey took about 3 days. That may sound quick, but those 3 days unfolded in a spacecraft no larger than a small room, moving through a silence and darkness unlike anything experienced on Earth. Astronauts described looking back and seeing Earth shrink to the size of a marble suspended in blackness, a sight both beautiful and deeply unsettling. For the first time, humans could see their home as a single, fragile world, isolated in space. That journey, as remarkable as it was, covered only a tiny fraction of the distances within the solar system. The moon is our closest neighbour, the first stepping stone outward, and yet it already stretches our sense of scale. Another way to appreciate this distance is to think about communication. When mission control spoke to astronauts on the moon, each message took about 1.3 seconds to travel one way. Conversations required patience, pauses, and careful timing. It was a subtle but constant reminder that even nearby space is not instantaneous, and yet in cosmic terms the moon is practically next door. To understand why, it helps to think about how gravity shapes the Earth-Moon system. The moon is bound to Earth by gravity, orbiting once every 27.3 days. But Earth also moves slightly in response to the moon's pull. In fact, both bodies orbit a common centre of mass, a point located inside Earth, but not at its centre. This gentle gravitational dance has been going on for billions of years. The tides in Earth's oceans are one visible result, rising and falling as the moon's gravity pulls on the water. Over very long periods of time, the interaction between Earth and Moon is slowly changing the system. The Moon is gradually moving farther away from Earth, drifting outward at a rate of about 3.8 centimetres per year, roughly the speed at which fingernails grow. It's a slow, almost imperceptible change, but over millions of years it adds up. Long ago, the Moon appeared larger in the sky than it does today, and in the distant future it will appear smaller. There's something quietly comforting about that steady motion. The idea that even the distances between worlds are not fixed, but evolve over time, shaped by gravity and motion. The journey to the moon also teaches us something about the nature of space itself. Between Earth and the moon, there is no air, no weather, no sound. Space is not like the thin air at the top of a mountain. It is a near-perfect vacuum, emptier than any environment we can create on Earth. That emptiness changes everything about travel. Without air, there is no drag to slow a spacecraft, but also no oxygen to breathe, no atmosphere to shield from radiation, no warmth to retain heat. Temperatures can swing wildly between sunlight and shadow. The silence is complete, broken only by vibrations inside the spacecraft itself. And yet, despite those challenges, humans made the journey, guided by mathematics, engineering, and an extraordinary amount of patience. It's worth pausing for a moment to consider how remarkable that is. For nearly all of human history, the moon was unreachable, a distant light in the sky. Then, within the span of a single generation, people walked on its surface, left footprints in its dust, and returned safely home. Those footprints are still there today. With no wind or rain to erase them, they may remain for millions of years, quiet marks of a brief human presence on another world. Looking at the moon from Earth now, it's easy to forget how far away it really is. Our eyes and brains are not well equipped to judge distances in the sky. The moon appears large because it is relatively close, but it still lies nearly 400,000 kilometres away, far beyond the reach of any aircraft, beyond the atmosphere, beyond the protective magnetic field that shields much of Earth's surface. And yet, in the scale of the solar system, that distance is only the first small step. To put it another way, if Earth and the moon were separated by 1 metre, the Sun would be about 400 metres away. Jupiter would be more than 2 kilometres distant. Neptune would be over 12 kilometres away, and the outer reaches of the solar system would stretch far beyond that, fading into distances difficult to imagine in everyday terms. So the journey to the moon, impressive as it is, barely begins to hint at the true size of the solar system. There's also something psychologically interesting about the moon as a reference point. It's close enough to feel familiar, yet far enough to remind us that space is vast. It sits at the boundary between the world we know and the wider universe beyond, a kind of threshold between Earth and everything else. For early astronauts, crossing that threshold was both exhilarating and sobering. As they moved farther from Earth, the planet filled less and less of the window, shrinking from a world into a sphere, then into a small disk against the blackness. One astronaut described the experience as realizing all at once that everything he had ever known, every place, every person, every memory, was contained in that small distant globe. It's a perspective that changes how you think about size, distance, and place. The moon may be far, but it's still close enough that Earth dominates the sky from its surface, hanging overhead as a large blue world, nearly 4 times the apparent size of the moon as seen from Earth. If you stood on the moon, Earth would not rise and set in the same way the moon does here. Instead, it would hover in roughly the same part of the sky, slowly changing phases, turning like a luminous marble suspended in darkness. That image, Earth seen from the moon, helps anchor our sense of scale in both directions. It reminds us that distances in space are large, but also that our home is just one small world among many. Trying to measure distances in space is a bit like trying to measure the width of an ocean while standing on the shore with nothing but a ruler. The scale is so far beyond everyday experience that our usual tools, kilometres and miles, quickly become awkward and difficult to use. The numbers grow so large that they lose their meaning. 1,000,000 kilometres sounds enormous, until you realise that light can travel that distance in just over 3 seconds, and suddenly the number feels smaller than it should. So astronomers had to learn, step by step, how to think about distance differently. They needed ways to measure the universe that made sense at scales, where ordinary intuition begins to slip. One of the earliest methods came from simple geometry, the same careful reasoning that allowed ancient scholars to measure the size of Earth. The key idea is something called parallax. You may have noticed this effect without realising it has a name. If you hold out your thumb at arm's length and close one eye, then switch eyes, your thumb seems to shift against the background. That apparent movement is parallax, and it happens because each eye sees the world from a slightly different angle. Astronomers realised long ago that the same principle could be used to measure the distance to nearby objects in space. Instead of using 2 eyes, they used Earth's motion around the Sun. 6 months apart, our planet is on opposite sides of its orbit, separated by about 300 million kilometres. From those 2 positions, nearby stars appear to shift slightly against the more distant background stars. By measuring that tiny shift and applying geometry, astronomers can calculate the star's distance. It's an elegant method, quiet and patient, relying on careful observation rather than dramatic technology. Even today, spacecraft like the Gaia Observatory continue to use parallax to map the positions and distances of millions of stars with extraordinary precision. But before astronomers could measure stars, they first had to measure the distances within the solar system itself. And that turned out to be a remarkable challenge. For centuries, people knew the relative order of the planets, but not their actual distances. They could see that Mars sometimes appeared brighter and closer than usual, and that Venus never strayed far from the Sun, but the scale of the system remained unknown. One of the breakthroughs came from observing the transit of Venus, a rare event in which Venus passes directly between Earth and the Sun, appearing as a small black dot moving across the solar disk. By timing this event from different locations on Earth, astronomers in the 18th century were able to use parallax to calculate the distance from Earth to the Sun with surprising accuracy. That distance, about 150 million kilometres, became the foundation for measuring everything else. Astronomers gave it a special name, the astronomical unit, or AU. The astronomical unit is one of the most useful ideas in astronomy because it provides a scale tailored to our own cosmic neighbourhood. Instead of saying Jupiter orbits at roughly 778 million kilometres from the Sun, it's much easier to say that Jupiter is about 5.2 astronomical units away. Neptune orbits at about 30 astronomical units. the numbers become smaller, easier to picture, and more meaningful in context. It's similar to how we use hours instead of seconds to measure long stretches of time. Both describe the same quantity, but one is easier to work with. Even with the astronomical unit, however, the solar system remains vast. Spacecraft travelling at tens of thousands of kilometres per hour still take years to reach the outer planets. Signals from distant probes take hours to return. The distances are large enough that time itself becomes part of the measurement. And that leads to another way astronomers think about distance: light travel time. Because light moves at a constant speed, it provides a natural ruler. Instead of saying that the Sun is 150 million kilometres away, we can say that sunlight takes about 8 minutes to reach Earth. Jupiter is about 40 to 50 light minutes from the Sun. Neptune is roughly 4 light hours away. This way of thinking has a quiet clarity to it. It connects distance with experience. When you feel sunlight on your face, you are feeling energy that left the Sun 8 minutes ago. When astronomers observe distant planets, they are seeing them as they were minutes or hours earlier. The farther we look, the further back in time we see. Within the solar system, these delays are modest, but they are real. When engineers send commands to spacecraft orbiting Mars, they must wait several minutes for a response. During that time, the spacecraft continues its work autonomously, guided by instructions sent long before. There is something both practical and poetic about that delay. The idea that even within our own planetary neighbourhood, communication is never instantaneous. Another important method for measuring distances in the solar system is radar ranging. This technique involves sending a radio signal toward a planet or asteroid, and timing how long it takes for the signal to bounce back. Because radio waves travel at the speed of light, the round-trip time reveals the distance with remarkable precision. Radar measurements of Venus in the mid-20th century helped refine the value of the astronomical unit and provided some of the most accurate measurements of planetary distances ever made. What's fascinating about radar ranging is its simplicity. The principle is the same as shouting in a canyon and listening for the echo, except the distances are measured in millions of kilometres, and the echoes are faint radio signals returning from distant worlds. Over time, astronomers developed an entire ladder of methods for measuring distance, each one suited to a different scale. Parallax works well for nearby stars. Standard candles, objects with known brightness, help measure more distant regions of the galaxy. Redshift reveals the expansion of the universe at the larger scales. But here in the solar system, the astronomical unit and light travel time remain the most intuitive tools. It's worth pausing for a moment to consider how extraordinary this is. Human beings, living on a small planet, have found ways to measure distances across billions of kilometres using nothing more than geometry, light, and careful observation. We've turned the universe into something measurable, not by shrinking it, but by expanding our understanding. And yet, even with these tools, distance in space can still feel abstract. Numbers alone rarely capture the emotional sense of scale. That's why astronomers and educators often use models to help people visualize the solar system. One common model imagines shrinking the Sun to the size of a grapefruit. At that scale, Earth would be a grain of sand about 15 meters away. Jupiter would be another small sphere about 75 meters from the grapefruit, and Neptune would be more than 400 meters away, far enough that you might lose sight of the model's center. Between these objects there would be long stretches of empty ground. Walking from one planet to another would take time, and that time helps the mind grasp the distances involved. Some museums and science centres have built walking-scale solar system models where each step represents millions of kilometres. Visitors begin at a large sculpture of the Sun and then walk, sometimes for several minutes, before reaching the first tiny marker representing Mercury. By the time they reach the outer planets, the walk may have covered hundreds of metres or more. People often remark on the same thing after experiencing these models: the emptiness, not the size of the planets, but the vast, quiet gaps between them. Those gaps are what truly define the solar system. Another subtle but important aspect of measuring space is uncertainty. Distances in astronomy are rarely perfectly precise. Orbits are slightly elliptical. Gravitational influences from other bodies cause small variations. Measurements improve over time as instruments become more accurate. Astronomy is, in many ways, a science of patience. Observations accumulate gradually. Data is refined. Models are updated. Over years and decades, our picture of the solar system becomes clearer and more detailed. Even now, spacecraft continue to refine our understanding. Missions to Mars, Jupiter and beyond provide precise tracking data that improves our knowledge of planetary positions and distances. The farther we explore, the better our measurements become. And yet, despite all this precision, there remains a sense of wonder in the simple fact that space is so large that it requires its own units of measurement, its own ways of thinking, its own patience. Once you begin to think in astronomical units and light minutes, the solar system starts to feel less like a collection of nearby worlds and more like a vast landscape, one where distances are measured not in steps or kilometres, but in the time it takes light to travel. Moving farther outward from Earth, the solar system begins to open up in a way that can feel surprising. Many of us grow up with diagrams showing the inner planets neatly lined up, orbiting the Sun in a compact arrangement, almost like beads on a string. Mercury sits closest, then Venus, then Earth, then Mars, all within what looks like a fairly small region before the asteroid belt appears like a boundary marking the next stage. But once you begin thinking in real distances instead of simplified drawings, that apparent closeness begins to dissolve. The inner solar system is not crowded at all. It is a region of scattered worlds, each separated by enormous stretches of empty space, each moving along its own path around the Sun, rarely coming anywhere near one another. To picture this more clearly, it helps to return briefly to the idea of the astronomical unit, the average distance between Earth and the Sun. At 1 astronomical unit, Earth sits comfortably in what astronomers call the habitable zone, where temperatures allow liquid water to exist. Mercury orbits at about 0.4 astronomical units, Venus at about 0.7 astronomical units, and Mars at about 1.5 astronomical units. Those numbers may look close together, but they conceal vast gaps. The distance from Earth to Venus at their closest approach is tens of millions of kilometres. The distance from Earth to Mars, even at its nearest, is still tens of millions more. Most of the time, the planets are much farther apart. Imagine placing the Sun in the centre of a large park as a sphere about 1 metre wide. Mercury would be a tiny speck roughly 40 metres away. Venus would be about 70 metres from the Sun. Earth would be about 100 metres away, and Mars roughly 150 metres out. Between each of those points, there would be nothing but open ground. If you were walking from one to another, the journey would feel long and quiet. There would be no visible path, no markers, only empty space between distant objects. That emptiness is the true character of the inner solar system. Mercury, the innermost planet, circles the Sun in just 88 days. It moves quickly, racing along its orbit at nearly 48 kilometers per second, faster than any other planet. From the Sun, Mercury would appear as a small, rocky world baked by intense heat, its surface marked by craters that have remained unchanged for billions of years. Because Mercury is so close to the Sun, it experiences extreme temperature swings. The side facing the Sun becomes incredibly hot, while the side in darkness grows intensely cold. With almost no atmosphere to distribute heat, the contrast is stark. It is a world of harsh sunlight and deep shadow, orbiting in silence. And yet, even Mercury is not close to the Sun in the way we might instinctively imagine. If the Sun were 1 metre across, Mercury's orbit would still be dozens of metres away, far enough that the Sun would appear large in its sky but not overwhelming. Moving outward, we reach Venus, often called Earth's sister planet because of its similar size. But in reality, Venus is a very different world, wrapped in thick clouds of carbon dioxide, with surface temperatures hot enough to melt lead. The atmosphere there is so dense that the pressure at the surface is more than 90 times that of Earth's atmosphere at sea level. Venus orbits the Sun more slowly than Mercury, taking about 225 Earth days to complete a single revolution. From space, it appears bright and reflective, its cloud layers bouncing sunlight back into space, making it one of the most brilliant objects in our night sky. Despite being the closest planet to Earth in terms of orbital distance, Venus is still unimaginably far away in human terms. Spacecraft travelling to Venus take months to arrive, following carefully calculated trajectories that use the motion of both planets to minimise fuel use. Then there is Earth, our reference point, a world with oceans, weather and life, orbiting in a relatively stable and temperate zone. From here, the distances between planets feel abstract, because we rarely experience them directly, but spacecraft remind us of their scale. Even a journey to Mars, our nearest outer neighbour, requires many months of travel. Mars itself orbits at about 1.5 astronomical units from the Sun. It is smaller than Earth, colder, with a thin atmosphere and vast deserts of iron-rich dust that give it its reddish colour. Robotic explorers have been studying Mars for decades, sending back images of ancient river valleys, towering volcanoes and landscapes that look strangely familiar, yet unmistakably alien. What's striking about Mars is not just its distance from Earth, but the variability of that distance. Because both planets move along their own orbits, sometimes they are on the same side of the Sun and relatively close, and other times they are on opposite sides, separated by hundreds of millions of kilometres. This changing geometry means that missions to Mars must be carefully timed, launching during windows that occur roughly every 26 months when the two planets are favourably aligned. Even then, the journey typically takes 6 to 9 months. That's another quiet reminder of scale. The nearest planet that humans might realistically visit lies many months away, even with modern technology. Looking at the inner solar system as a whole, what stands out is how small the planets are compared to the distances between them. If you were drifting through this region in a spacecraft, you could travel for days or weeks without seeing anything larger than a distant point of light. Space is not like the crowded scenes often shown in science fiction, where ships weave between planets and asteroids in a matter of minutes. In reality, the solar system is mostly empty. The planets are separated by vast expanses of vacuum, and encounters between objects are rare on human timescales. Even the asteroid belt, which many people imagine as a dense field of tumbling rocks, is mostly empty space. The asteroids are spread over such a large region that a spacecraft can pass through without seeing any nearby objects at all, unless it deliberately navigates toward one. That sense of isolation becomes clearer when you consider how the planets would appear from one another. From Mars, Earth is visible as a bright star-like point. From Venus, Earth appears similarly small, though sometimes bright enough to cast faint shadows. None of the planets loom large in one another's skies the way the Moon appears from Earth. The distances are simply too great. There's also a deeper pattern to the inner solar system, one that astronomers believe reflects its formation billions of years ago. Close to the Sun, temperatures in the early solar nebula were high, allowing only rock and metal to condense into solid bodies. Farther out, beyond a certain distance, ices could form, leading to the creation of much larger, gas-rich planets. This is why the inner planets are small and rocky, while the outer planets are enormous and composed largely of gas and ice. The boundary between these regions lies somewhere beyond Mars, near the area we now call the asteroid belt. Understanding that history helps explain why the inner solar system looks the way it does. A handful of relatively small worlds orbiting in a broad, mostly empty region, with the Sun dominating everything at the centre. The Sun itself, even at these distances, remains the most prominent object in the sky of every inner planet. From Mercury, it appears more than twice as wide as it does from Earth. From Mars, it looks slightly smaller but still brilliant, casting sharp shadows across the dusty surface. That steady presence of the Sun ties the inner planets together. Each one is bound by its gravity, following an orbit determined by a balance between motion and attraction, falling endlessly around the Sun rather than into it. It's a graceful kind of motion, silent and continuous, going on for billions of years without interruption. Sometimes it helps to think of the inner solar system not as a cluster of planets, but as a vast circular track, with each world moving along its lane at its own pace. Mercury races along the innermost track, completing a lap in less than 3 months. Venus takes about 7.5 months. Earth takes a year. Mars takes nearly 2. If you could watch from far above, you would see a slow, intricate dance, each planet tracing its path, sometimes drawing closer to another, sometimes drifting farther away, all bound by the same central star. Somewhere beyond the orbit of Mars, the inner solar system begins to give way to something different. Up to this point, the planets we've considered, Mercury, Venus, Earth, and Mars, feel almost like neighbours in a broad but still recognisable region. The distances are large, but they are not yet overwhelming. The travel times between worlds, measured in months, are still within the range of human planning and imagination. Then, gradually, you reach a region where the sense of scale begins to change. This region is known as the asteroid belt, a vast zone stretching roughly from about 2.1 to 3.3 astronomical units from the Sun. On a diagram, it often appears as a thick ring of rocks crowded together, sometimes shown as a dense field of tumbling boulders, as if spacecraft would have to weave carefully to avoid collisions at every turn. In reality, it is nothing like that. The asteroid belt is enormous, and the objects within it are separated by distances so great that a spacecraft can pass through without encountering anything at all, unless it deliberately aims for a target. The typical distance between sizable asteroids can be hundreds of thousands or even millions of kilometers, so why does the asteroid belt matter so much when thinking about the size of the solar system? Because crossing it marks the first moment when distances begin to feel truly vast, not just large, but expansive in a way that reshapes intuition. The belt itself contains millions of objects, ranging from tiny grains of dust to dwarf planets hundreds of kilometers across. The largest body there is Ceres, about 940 kilometers in diameter, large enough to be spherical under its own gravity, and now officially classified as a dwarf planet. Other notable asteroids like Vesta, Pallas, and Hygeia are substantial worlds in their own right, remnants of the early solar system that never merged into a full-size planet. Astronomers believe that the asteroid belt formed from material that was prevented from coalescing into a planet by the gravitational influence of Jupiter. Jupiter's enormous mass stirred the region, increasing the velocities of nearby objects and making collisions more destructive than constructive. Instead of forming a single large body, the material remained scattered, leaving behind the belt we see today. But what's most striking about the asteroid belt is not the number of objects in it, but the amount of space between them. If you imagine shrinking the solar system down to a scale where Earth's orbit is about 100 meters from the Sun, the asteroid belt would begin roughly 210 meters out and extend to about 330 meters. Within that broad annulus, the asteroids themselves would be tiny, often no larger than grains of sand or pebbles at that scale, separated by distances of many meters or more. Walking across that region would feel like crossing a vast empty field where only occasionally you might notice a small stone on the ground. Spacecraft that have travelled through the asteroid belt, such as the Pioneer and Voyager probes, did not encounter swarms of rocks or hazardous clouds. They passed through quietly, entering and leaving the region without incident. Later missions like Dawn, which orbited both Vesta and Ceres, demonstrated just how sparse the belt truly is. And yet, even though it is mostly empty, the asteroid belt serves as an important psychological boundary. It marks the transition between the inner rocky planets and the outer giants, between a region where the Sun still feels relatively close and one where distances begin to stretch dramatically. To appreciate this, consider the distance from Mars to the inner edge of the asteroid belt. Even at its closest, Mars lies about 1.5 astronomical units from the Sun, while the belt begins beyond 2 astronomical units. That gap alone is roughly the same as the distance from Earth to the Sun. In other words, there is an entire Earth-Sun distance of mostly empty space between Mars and the asteroids. And then the belt itself spans another astronomical unit or more. This is where the true scale of the solar system starts to emerge. The inner planets, which once seemed widely spaced, begin to feel clustered together near the Sun, like a small group of stones at the centre of a wide plain. Another way to sense this scale is to think about travel times. A spacecraft heading toward Jupiter must first cross the distance to Mars, then traverse the wide gulf to the asteroid belt, then pass through it, and only then continue outward into even greater distances. Each stage takes months or years. Signals sent from spacecraft in the belt take tens of minutes to reach Earth. The Sun, still bright, appears noticeably smaller than it does from Earth, though it remains the dominant light in the sky. For early spacecraft engineers, reaching the asteroid belt was once considered a significant milestone. It marked the first step into the deeper solar system, a point where missions moved beyond the relatively familiar territory near Earth and began exploring regions never before visited. There is also something quietly evocative about the asteroid belt as a place. It is a region of remnants, fragments left over from the formation of planets billions of years ago. Each asteroid is a time capsule, preserving clues about the early solar system, about the processes that built worlds and shaped their orbits. Some asteroids are rich in metals, others in silicates, others in carbon compounds. Some contain water locked in minerals, hinting at the role these objects may have played in delivering water to the early Earth. So while the belt may seem empty, it is far from uninteresting. It is a region filled with history, scattered across enormous distances. Another subtle effect of moving outward through the asteroid belt is the changing appearance of the Sun. From Earth, the Sun dominates the sky, bright and intense. From Mars, it is already slightly smaller. From the middle of the asteroid belt, it appears noticeably reduced, still brilliant but no longer overwhelming. Light and heat diminish with distance, following the inverse square law. Double the distance from the Sun, and the sunlight becomes only 1/4 as intense. By the time you reach the outer edge of the asteroid belt, sunlight is less than 1/5 as strong as it is on Earth. That gradual fading of sunlight adds to the sense of moving outward, of leaving the inner solar system behind and entering a region where the Sun's warmth and brightness are less dominant. Crossing the asteroid belt, then, is not just a physical journey, but a conceptual one. It is the point where the solar system begins to reveal its true proportions, where the inner planets shrink into a compact region near the Sun, and the outer system opens up into distances that are harder and harder to imagine. If you are travelling outward, this is the moment when the familiar begins to fade, when the Sun grows smaller, when the gaps between worlds widen, and when the realization begins to settle in that the solar system is far larger than it first appeared. Beyond the scattered expanse of the asteroid belt, the character of the solar system changes in a way that is difficult to appreciate until you really slow down and think about it. Up to this point, the planets we've talked about have been relatively small, rocky, and not so different from one another in size. The distances between them have been large, certainly, but still manageable in the sense that a spacecraft can cross them in months or a few years. Then Jupiter comes into view, and the scale of everything shifts. Jupiter is enormous, not just slightly larger than Earth or Mars, but truly immense. Its diameter is about 143,000 kilometres, more than 11 times that of Earth. You could line up more than 11 Earths side by side across Jupiter's width, and there would still be a little room left over. In terms of volume, Jupiter could hold more than 1,300 Earths inside it. And yet, despite that size, Jupiter is still only a small part of the solar system. What makes its presence so important is not just its physical scale, but its distance from the Sun and from the inner planets. Jupiter orbits at an average distance of about 5.2 astronomical units. That means it is more than 5 times farther from the Sun than Earth is. Light from the Sun takes about 43 minutes to reach Jupiter, compared to just over 8 minutes to reach Earth. That difference alone begins to stretch the imagination. If you were standing on a spacecraft approaching Jupiter, looking back toward the Sun, it would already appear noticeably smaller than it does from Earth, though still bright enough to dominate the sky. The warmth of sunlight would be much weaker. Solar panels, so effective near Earth, become less practical out there, which is why many spacecraft travelling to Jupiter rely on nuclear power instead. The journey to Jupiter also takes time in a way that feels more substantial. Spacecraft do not simply fly straight there in a few weeks. They follow carefully planned trajectories, sometimes using gravity assist from other planets to gain speed. Even with these techniques, a mission to Jupiter typically takes several years. That long travel time reveals something important. The solar system is not just large in distance, but in duration. To move through it requires patience. Signals take longer to travel. Journeys unfold slowly. Exploration becomes measured not in days or months, but in years and decades. There's also a striking change in how space itself feels as you move outward. Inside the orbit of Mars, the Sun dominates everything. Its light fills the sky. Its warmth defines the environment of every world. But by the time you reach Jupiter, the Sun has begun to lose some of that dominance. It is still powerful, still the central force shaping the system, but it no longer feels close. The sky grows darker. The distances between objects become more apparent. The inner planets, clustered near the Sun, would appear as faint points of light, barely distinguishable from stars. Jupiter itself, however, more than makes up for the fading presence of the Sun. It is a world of immense storms, swirling cloud bands, and a magnetic field so powerful that it traps radiation in vast belts surrounding the planet. Its Great Red Spot, a storm larger than Earth, has been raging for centuries. Orbiting Jupiter is a system of moons that almost feels like a miniature solar system of its own. The 4 largest moons, Io, Europa, Ganymede, and Callisto, are substantial worlds in their own right. Ganymede is larger than the planet Mercury. Europa hides an ocean beneath its icy surface. Io is the most volcanically active world known, its surface constantly reshaped by eruptions driven by tidal forces. Standing in the Jovian system, you would see multiple moons rising and setting, casting shadows on the planet's cloud tops, forming a dynamic and ever-changing sky. And yet, as impressive as Jupiter is, what truly begins to feel unreal is not the planet itself, but the distances beyond it. Because once you reach Jupiter, you're still only partway through the planetary region of the solar system. Saturn lies nearly twice as far from the Sun as Jupiter does. Uranus lies nearly twice as far as Saturn. Neptune lies still farther, at about 30 astronomical units from the Sun. Each step outward multiplies the scale in a way that becomes increasingly difficult to grasp. The gaps between orbits widen. The time required to travel between them grows longer and longer. Light itself begins to take hours to cross the distances involved. To put this into perspective, imagine that the distance from the Sun to Earth were reduced to 1 metre. At that scale, Jupiter would be just over 5 metres away. Saturn would be about 10 metres out. Uranus would be nearly 20 metres distant, and Neptune about 30 metres away. Those numbers may not sound enormous, but remember that at this scale Earth itself would be only about 9 millimetres across, smaller than a pea. The planets would be tiny, scattered objects separated by long stretches of empty space, and beyond Neptune, the distances continue to grow. One of the most striking things about the outer solar system is how empty it is. Between Jupiter and Saturn, there is an average gap of more than 650 million kilometres. Between Saturn and Uranus, the distance is even greater. These are expanses so vast that if you were travelling through them, days or weeks could pass without seeing anything but the distant sun and the faint stars. There is a kind of quiet to that emptiness, a stillness that is hard to imagine from our busy, crowded world. Another way to sense this scale is to think about communication again. Signals sent from spacecraft near Jupiter take roughly 35 to 50 minutes to reach Earth, depending on the relative positions of the planets. That means every command, every piece of data, every image arrives with a significant delay. Engineers operating missions in the outer solar system must plan carefully, anticipating problems long before they occur, because real-time control becomes impossible. Spacecraft must often make decisions on their own, guided by instructions sent hours earlier. This separation in time and distance reinforces the feeling that these regions are remote in a way that Mars and the Moon are not. They belong to a different scale of exploration. Jupiter also marks an important boundary in another sense. Its immense gravity has shaped the solar system in profound ways. It acts as a kind of gatekeeper, influencing the paths of comets, deflecting some toward the inner planets, while ejecting others entirely from the solar system. Without Jupiter, the history of Earth might have been very different. Some scientists believe that Jupiter's presence has reduced the number of catastrophic impacts in the inner solar system, though the details are still debated. What is certain is that Jupiter's gravitational reach extends far beyond its own orbit, shaping regions millions of kilometres away. In that sense, Jupiter is not just another planet. It is a dominant feature of the solar system, second only to the Sun in its influence. And yet, even Jupiter is only one step along a much longer journey outward. When spacecraft like Voyager 1 and Voyager 2 passed Jupiter in the late 1970s, they used its gravity to slingshot themselves towards Saturn and beyond, gaining tremendous speed. Those missions revealed something that is easy to overlook when thinking about the solar system from a distance. Reaching Jupiter is not the end of the journey. It is the beginning of a much longer passage into regions where sunlight grows faint and distances become harder and harder to imagine. Out there, the sun shrinks to a brilliant star, still brighter than any other, but no longer filling the sky. Shadows soften. The energy available from sunlight drops dramatically. Temperatures fall. And yet, even in that cold and distant realm, the solar system continues, stretching outward far beyond the orbits of the giant planets, into regions filled with icy bodies and distant remnants of its formation. There is a psychological shift that happens when you think about these distances carefully. At first, the solar system seems like a collection of planets orbiting a star, but as you move outward, it begins to feel more like a vast territory, a region of space defined not by objects, but by the enormous gaps between them. Those gaps are the true measure of its size. Jupiter helps reveal that truth because it stands at a kind of threshold. Inside its orbit, the planets are relatively close together, clustered near the Sun. Beyond Jupiter, the solar system opens up, the distances widen, and the sense of scale deepens. If you were travelling outward, this would be the point where the journey begins to feel truly long, where turning back would already require years, where the inner planets would fade into faint points of light near the Sun. Continuing outward from Jupiter, the solar system becomes quieter in a way that is difficult to appreciate until you slow down and imagine the journey carefully. Jupiter already feels distant, already marks a region where the Sun begins to shrink and travel, times stretch into years. But beyond Jupiter lies an even larger realm, where the spaces between worlds grow wider, the sunlight fades further, and the sense of isolation deepens with every astronomical unit. The next world outward is Saturn, orbiting at an average distance of about 9.5 astronomical units from the Sun. That means Saturn is nearly twice as far from the Sun as Jupiter is, and about 10 times farther than Earth. Sunlight there is only about 1% as strong as it is on Earth. The Sun, seen from Saturn, still shines brightly, but it appears smaller, less dominant, more like an intense lamp than the overwhelming disk we see from home. Saturn is famous for its rings, wide and luminous, stretching tens of thousands of kilometres across, yet astonishingly thin, in many places only a few tens of metres thick. From a distance, the rings appear solid, like a shining disk encircling the planet, but up close they are made of countless particles of ice and rock, each orbiting Saturn independently, each following its own path in a silent and delicate dance. If you could drift among those ring particles, the experience would not feel crowded. The pieces are separated by distances that, in many regions, are measured in meters or even tens of meters. It would feel more like floating in a slow-moving snowstorm than navigating a solid structure. Saturn's moons add another layer of complexity to this distant system. Titan, its largest moon, is larger than the planet Mercury, and possesses a thick atmosphere rich in nitrogen, with lakes and rivers not of water, but of liquid methane and ethane. Enceladus, another moon, hides a global ocean beneath its icy crust and sends plumes of water vapour into space, hinting at the possibility of habitable environments far from the Sun's warmth. Standing in orbit around Saturn, looking outward, the solar system would already feel enormous. Jupiter would be a distant point of light. The inner planets would be invisible without telescopes. Earth itself would appear as nothing more than a pale dot, lost among the stars. And yet, even at Saturn's orbit, you're still far from the edge of the planetary system. Beyond Saturn lies Uranus, a world so distant that sunlight takes nearly 3 hours to reach it. Uranus orbits at about 19 astronomical units from the Sun, roughly twice the distance of Saturn. By the time you arrive there, the Sun appears small and sharp, a brilliant star rather than a blazing disk. Uranus is an unusual planet in many ways. It rotates on its side, tilted by about 98 degrees so that its poles spend long periods facing directly toward or away from the Sun. Seasons there last for decades. For years at a time, one hemisphere remains in continuous daylight while the other remains in darkness. The colour of Uranus, a pale blue-green, comes from methane in its atmosphere, which absorbs red light and reflects blue. It is a quiet world, without the dramatic banding of Jupiter or the bright rings of Saturn. Its rings are faint and narrow, discovered only in the late 20th century. The distance to Uranus reveals something important about the outer solar system. The gaps between planets are not just large, they are immense. The distance from Saturn to Uranus is about 1.4 billion kilometres, nearly 10 times the distance from Earth to the Sun. Crossing that gulf takes spacecraft many years. During that long passage, there is almost nothing to see. The sun shrinks slowly behind you, the stars remain fixed, the vastness between worlds becomes more apparent than ever, and still, beyond Uranus, there is Neptune. Neptune orbits at about 30 astronomical units from the Sun, more than 30 times farther out than Earth. Sunlight takes about 4 hours to reach Neptune, and by the time it arrives, it is faint, only about 1/900th as intense as the sunlight on Earth. From Neptune's clouds, the Sun would appear no larger than a bright star, though still bright enough to cast faint shadows. The sky would be dark even at noon, illuminated only by that distant point of light. Neptune is a world of deep blue colour and powerful winds, some of the fastest in the solar system, reaching speeds of more than 2,000 kilometers per hour. Storm systems appear and disappear in its atmosphere, driven by internal heat rather than sunlight, because so little solar energy reaches that far. Its largest moon, Triton, orbits in the opposite direction of Neptune's rotation, suggesting that it was once an independent object captured by Neptune's gravity. Triton's surface is cold beyond ordinary experience, with temperatures near -235 degrees Celsius. Nitrogen geysers occasionally erupt there, sending dark plumes across the frozen landscape. Standing in the outer solar system, somewhere near Neptune, the sense of silence would be profound. The sun would be distant, the inner planets invisible, the stars sharp and steady, unblinking in the darkness. There is a kind of stillness that comes with such distances, a feeling that space is no longer just large, but immense in a way that begins to challenge imagination itself. And yet, even Neptune does not mark the end of the solar system. That's one of the most surprising facts about our cosmic neighbourhood. The region of planets that most people think of when they imagine the solar system, from Mercury to Neptune, occupies only a small portion of its true extent. Beyond Neptune lies another vast region, filled with icy bodies and dwarf planets, a zone that stretches tens of astronomical units farther out. This region is known as the Kuiper Belt, and it is home to Pluto and many other distant worlds. To appreciate the scale involved, consider this. If the distance from the Sun to Neptune were represented by 30 steps, the Kuiper Belt would extend many steps farther still, and beyond that lies an even more distant region, the hypothetical Oort cloud, which may stretch tens of thousands of astronomical units into space. In other words, the planetary system we've just travelled through, from Mercury to Neptune, is only the inner core of a much larger structure. There is something quietly humbling about that realisation. The planets feel so far apart, their orbits so wide, their travel times so long, and yet they occupy only a small fraction of the Sun's gravitational domain. Another way to sense the scale is to think about the Voyager spacecraft. Voyager 2, the only spacecraft to have visited Uranus and Neptune, was launched in 1977. It reached Neptune in 1989, 12 years later. 12 years of travel to cross the outer planetary system, moving faster than any human-made object had before. And even after passing Neptune, Voyager continued onward, still travelling today, decades later, moving through the outermost regions of the solar system. That journey reveals the true size of our cosmic neighbourhood. It is not a compact cluster of planets, but a vast expanse of space, stretching far beyond the worlds we can easily name. The outer planets, Saturn, Uranus, and Neptune, serve as milestones along that expanse, markers of distance rather than boundaries. They remind us that the solar system is not defined by where the planets end, but by where the Sun's influence fades into the broader galaxy. If you were travelling outward, passing Neptune, you would not encounter a wall or a sudden change. The planets would simply fall behind, one by one, until the nearest large world was billions of kilometres away, and the solar system would begin to feel less like a system of planets and more like a vast region of space. Beyond the orbit of Neptune, the solar system does not suddenly end. There is no clear boundary, no abrupt transition from planets to empty space. Instead, the environment changes gradually, almost quietly, as though the solar system is thinning out rather than stopping. This region just beyond Neptune is known as the Kuiper Belt, a vast expanse filled with icy bodies, dwarf planets, and countless smaller fragments left over from the formation of the solar system. It begins at roughly 30 astronomical units from the Sun, and extends outward to about 50 astronomical units, though its edges are not perfectly sharp. At first glance, It might be tempting to imagine the Kuiper belt as similar to the asteroid belt, just farther away and colder, but the comparison only goes so far. The asteroid belt lies between the inner and outer planets, relatively narrow in scale, influenced strongly by Jupiter's gravity. The Kuiper belt, by contrast, is far larger and far more distant, occupying a region of space that dwarfs the entire inner solar system. To appreciate this, it helps to think about the distances involved. Neptune orbits at about 30 astronomical units. The outer edge of the Kuiper belt may lie near 50 astronomical units. That means the belt itself is about 20 astronomical units wide, nearly the same span as the entire region from the Sun to Uranus. And yet, despite its enormous size, the Kuiper belt is mostly empty. The objects within it are separated by vast distances, much like the asteroids, but on an even grander scale. A spacecraft travelling through the belt might pass for weeks or months without seeing anything larger than a faint speck in the distance. This emptiness is part of what makes the Kuiper belt so fascinating. It is not a crowded ring of debris, but a sparse, cold frontier, where the sun's influence is still present but noticeably weaker. Sunlight there is faint, about 1/2000th as intense as on Earth. The sun itself appears small, bright, but no longer dominant in the sky. Shadows are soft. The warmth of sunlight is barely perceptible. Temperatures in the Kuiper belt are extremely low, often below -220 degrees Celsius. And yet, even in this cold and distant region, there are worlds,